Hello, I'm Professor Steve Miller. Welcome back to Introduction to Computational Fluid Dynamics. Today we have a special topics class on aeroacoustics and its use with CFD. We'll be talking about how aeroacoustics is, as it came to being its own subject, and how it's combined with CFD today. CFD has made a tremendous impact on the field of aeroacoustics. It's a specialized field, of course, in aerospace engineering. In this class, we'll be looking at some of the results from a review article on computational aeroacoustics called Progress on Nonlinear Problems on Sound Generation by Colonius and Lilley. We'll be looking at particular classifications of computational aeroacoustics problems, simulations themselves, particular computational issues, and examples. We'll look at a lot of examples of computational problems and just give you an overview of the field and how CFD might fit in. That is to say, CFD has developed specific and specialized techniques to handle aeroacoustics problems today. You can't just typically take a CFD code out of the box, so to speak, and apply it successfully to an aeroacoustics problem. It's going to take a lot of specialized considerations. It's one example of many fields which have been combined with CFD today to make great progress. Now, computational aeroacoustics, that is, performing aeroacoustics problems numerically, will be the combination of using aeroacoustics and CFD. Its development is really quite independent of computational fluid dynamics, but nonetheless, the two fields have really merged. Highly specialized numerical methods were developed to capture both the acoustic waves and fluid dynamics. We can go back to 1858 and look at a particular set of experiments, LeConte. And LeConte noticed that cellos altered the gas-fired jets. These types of jets were formed on the right here. On the left is an unaltered jet, and the one with combustion in, of course, it's reacting like a flame. And on the right is another one where acoustic waves were triggering instabilities within the flow. These very, very, very tiny little acoustic waves altered the flow field greatly. And so the smallest of perturbations in a fluid dynamic flow must be accounted for aeroacoustic problems. These stabilities were seen in general by people watching concerts with their flames dancing to the notes. Now, a fellow named Tyndall conducted experiments and noted that smooth flames of, say, 24 inches reduced to only 7 inches when particular keys were shaken on the keyboard. Nonetheless, it's shown today that the transient irregularities on these surfaces of smooth jets is created by the noise. It's one of many examples of flow instability altered by, say, acoustic waves, which is part of the field, of course, of aeroacoustics. Aeroacoustics today is very important because of, for instance, jet noise. And jet noise might be separated into two categories, military and commercial. On the top, you see a United States Navy carrier with an aircraft on the deck, and you see there's a large plume containing shocks and supersonic turbulence in the exhaust. There's many personnel staying right next to them. Nonetheless, today, Navy personnel lose their hearing or some have some permanent hearing damage within about 10 to 15 minutes of being on the deck in these full operations. They also have, of course, tinnitus and other hearing effects and psychological effects from noise. In the lower right, you see a contemporary aircraft engine with teeth or chevrons on the nozzle, and these chevrons are reduced to reduce noise on commercial aircraft, to reduce noise around, say, airport communities or airportal communities. So this is another example of where aeroacoustics has directly altered the aerospace engineering and aeronautics. Aeroacoustics also exists in the aerospace industry itself, the space side of it. Here on the right, you see a particular rocket from Marshall Space Flight Center from Counter in Houston. This is actually a scale model test. And the noise around launch pad structure is actually so loud that it damages the launch pad structure and might even damage the rocket itself and lead to flight vehicle failure. Acoustics around launch pad structures has also altered and destroyed satellite systems. So when they reached orbit, unfortunately, they couldn't be activated and work. So that's another huge problem with the aeroacoustics problem. Here's one particular flow field of a jet, and we've talked about these in this class in CFD. Here's the nozzle, it's a slur, and flow moves from left to right, and you see the shock waves, which are lines, and you see the turbulence, which is, of course, granular looking in the Chevrons. There's also expansion waves. This is one of the most complicated problems to study in CFD because it contains every type of flow field there is that we usually study, and it generates very complicated acoustic radiation. So you have to completely understand from the fluid dynamics and mathematics of the jet problem before you can study the acoustics problem associated with jets to solve the problems in the aeronautics and space industry. A lot of the aeroacoustics work was actually traced back, well, not directly, but with particular solutions of what we call acoustic analogies to a fellow named George Green. George Green was basically a teenager when he became interested in mathematics, and he was self-taught, and he found many mathematical theories that we still use today, including Green's theorem, potential functions, and of course, for aeroacoustics, the famous Green function. Another important person in the heritage and development of aeroacoustics was, of course, Jeffrey Lilley, who was my advisor's advisor, and he was the one who originally came up with the ideas of chevrons and teeth. He actually did it for an open jet wind tunnel, but you might see some military or commercial aircraft with these types of structures on the rear end, that is the lip of the nozzle, and you'll see that these are there strictly to reduce noise and without hurting thrust. It's a very difficult problem that's under current research today and has been a big part of my career. Now, traditionally, the challenge of aeroacoustics can be traced to the fact that the acoustic waves are an unstudied fluid dynamic process in their generation. And turbulence modeling such as RANs or unsteady RANs and LES often filter out the scales that lead to acoustic radiation. So the fine scale turbulence would be averaged away with RANs or filtered away with LES. And so these typical approaches cannot typically be used directly for aeroacoustics problems without some modification. We do note that these acoustic waves propagate directly and coherently with very low attenuation and viscous effects over long distances. Therefore, like the artificial dissipations in your typical commercial solvers, may be inappropriate to handle aeroacoustic problems. We also note that acoustics is a very low efficiency mechanism of generation. For example, when a 747 takes off under full power, with 4-engine 747 of course, most of the energy from the engines will be dissipated in heat. The amount of acoustic radiation in terms of total energy from a 747 on takeoff is only enough to boil a single hard-boiled egg. It's very little energy, and so the acoustic radiation is very inefficient relative to the conversion of the fluid dynamic energy into heat. If we can look at computational aeroacoustics itself, we might view it as a separation of linear to nonlinear problems. There's many nonlinear acoustic problems. When the acoustic intensity from, say, a fluid dynamic flow becomes large enough, it'll start to propagate in a nonlinear fashion. This is a major problem and breakdowns in many techniques. And so thankfully, some problems can be examined as a linear acoustics problem, where we can separate and look at the solution as a separate linear acoustic solution that's coupled with the fluid dynamic solution. This is often done today, and it's advanced the field a lot. But unfortunately, there's some sources like a sonic boom problem or a very large jet flow, which of course will not allow us to linearize problems. The nonlinear problem is even more complicated. On the right, I have a typical N wave, so a very simple sine wave of acoustics. If it's high enough amplitude, or if it travels far enough distance without being dissipated, will eventually coalesce and become this N-type wave. And so this is its own type of shock, and many people are not aware that a simple sine wave or acoustic wave can actually become a shock. That's very counterintuitive, but of course there's mathematical equations and proofs to show this is true. And we see this in nature and, of course, in engineering. There's all kinds of areas that must be accounted for, which I've written on the left for these types of problems. You have to understand perhaps atmospheric turbulence, the nonlinear steepening of disturbances, the decaying of these waves, and of course all the nonlinear mechanisms themselves which might generate more noise if especially these waves are interacting with other turbulent fields or other solid structures. The linear problems can be looked at as an example as like a trailing edge noise. So when you have a flow over airfoil, the wake of the airfoil actually generates something like a dipole noise. This is shown in the lower right figure. Here's something like the study solution, and here's the unstudied solution. As the flow and turbulent boundary layers merge, they create a humongous noise source. On the left, we can see one type of spectrum. On the x-axis is frequency, and the y-axis is something like the power spectral density in a log plot. And you can see it creates something like a spectrum of noise. This is the intensity, essentially, of the noise as a function of frequency. And so these types of noise sources, especially if they're from turbulence, create broadband, high-intensity turbulent noise. This is also a major problem for the aerospace industry and should be mitigated. This is a quieter problem, but there's many more louder problems. Let's look at a nonlinear problem. Say we have a turbulent jet. In the lower right, we show contours of a turbulent jet. Here's the high-speed jet flow moving from left to right. This is like the exhaust from an engine. You can see the shock cell structure within the plume, and you see acoustic waves rating in the contoured regions. This, of course, can be predicted with CFD or be performed with experiments. The upper right figure shows basically an outline or caricature, if you will, of the processes in the turbulent jet in the lower right. In the lower left, we have a sound pressure level, which is like the amount of energy, pressure squared per unit hertz, normalized with a logarithmic scale, in sound pressure level based on dB, with non-dimensional frequency on the x-axis. These lines represent a particular two large eddy simulations from the result on the right with one particular empirical formula as the dashed line. So you can see we can combine LES with acoustic theory to predict the acoustic noise. This is a rather complicated approach, and it's a whole field in itself, and many of my students have studied this particular interesting problem. The nonlinear cases for the jet can also be seen here. Say we have a Mach 0.9 jet. In the upper right-hand corner, we write the velocity along the center line of the axis of the jet. On the x-axis, we have a normalized axial position, the streamwise position of the flow. The points and lines represent experiments and simulations respectively. So our CFD, like in our class example, has given us very good predictions. In the lower left, we show a turbulence intensity, U prime along the core divided by the jet velocity. Fully expanded velocity divided by, of course, the distance from the nozzle exit. We show, once again, LES predictions and experiments. In the lower right, we can use this data to create predictions themselves. This is a polar plot, which we talked about earlier in this class. The 0 degree is the downstream direction. As you go up to 180 degrees would be the forward direction relative to an aircraft. Aircraft might sit in the middle. This line and points represent the same predictions, and so there's some directivity with noise. Many noise sources contain some particular type of directivity. Outside of computational fluid dynamics, and something which eventually has been combined with computational fluid dynamics, is the all-famous acoustic analogy. The acoustic analogy is a particular solution, a statistical solution for a very specific quantity and type of flow field of the Navier-Stokes equations. The Navier-Stokes equations are rearranged without assumption into a left-hand side wave propagating operator, and right-hand side source terms, or equivalent sources. Many famous forms of this equation exist today, but it was indeed pioneered by Lighthill in the 1950s, who's, of course, a very famous mathematician. These are a type of original analytical methods in acoustics and might be viewed as the birth of aeroacoustics. Lighthill's acoustic analogy is shown on the right. This is the particular wave equation in 3 dimensions, and the right-hand side represents the double divergence of the stress tensor, which we call the Lighthill stress tensor, which is written here. All these variables should be familiar to you after our fluid dynamic review session, so you can see this is a very simple and technical form of the equation. We can also solve this numerically and combine it with computational fluid dynamics to form, of course, a unique field called computational aeroacoustics. Now, there's different classifications of aeroacoustics. We can go back and do direct numerical simulation or large eddy simulation, and these would result in, if we're putting and measuring a pressure outside the turbulent field, the acoustic fluctuating pressures, and we calculate these directly. This is very, very computationally intensive and expensive, and so this is not typically done today except for research studies. There's also hybrid methods which are much more popular. We might combine DNS and LES with acoustic analogies, which is becoming very popular. Simpler methods like vortex CFD methods with the acoustic analogies. We might try and split our flow field into an incompressible part and compressible part and solve the problem in that methodology. We might linearize our equations to study the linear waves coming out of a mean flow. like the linearized Euler equation approach, where we linearize the equations and solve the linearized form about a base flow. And we might use an LAS method. Now, numerical discretization in computational or aeroacoustics is very important. There has to be the effect of preserving the dispersion properties of waves. On this particular plot, I've shown the famous dispersion relation preservation numerical scheme, which is a finite difference scheme of course, Professor Chris Tam of Florida State University. In this particular plot, it's very important to note that there's a particular wave number and its dispersion property which are being preserved. Ideally, this would be a relation which is linear and conserved. Of course, if we apply standard 5-point or 7th point central differences, we would only find a particular relationship that goes where my cursor is moving. With dispersion relation preservation numerical schemes, we've optimized the coefficients to preserve this relationship. In aeroacoustics, if we're just doing the work computationally, we would use a DRP scheme to try and preserve the dispersion relation of acoustics. This is never done in a conventional CFD solver, and is one of the core reasons why conventional CFD is not appropriate for acoustics problems. Aeroacoustics also requires very specialized specifications of boundary conditions. The boundary conditions for typical CFD, which we talked about in this class, are not necessarily appropriate for an acoustics-based CFD problem. If we're doing full Navier-Stokes equations and want to capture the acoustics in the CFD, we have to have specialized boundary conditions. The boundary conditions, in addition to their normal properties, must also handle all the effects of the acoustic waves entering the domain and leaving the domain. They should be specified or allowed to leave without reflection. This is a very difficult topic which many people have spent their careers on, the boundary conditions for acoustics and electromagnetics. In the lower part of the page, I've shown one particular figure of a cavity flow problem, which of course we talked about in this class. But have you considered how the acoustic waves are generated in the flow and how they leave and enter the domain? This type of figure here, which I'll let you review quickly, shows these types of effects. Another famous problem is the landing gear problem. Imagine the complicated CFD that we have to perform around the landing gear. Well, here it is. First, we have to create a computational domain. These top plots show, of course, the original computational domain, which reserves all the boundary layers, but not the wake behind the landing gear itself, which of course creates a lot of noise. If we want to study from noise from the landing gear, we not only have to have a really good CFD simulation, which is time resolved, but we also have to have an acoustic method to predict the noise from it. This is one such example. Here's the figure showing the flow and the wake around the landing gear through one cut plane in the flow. In the lower left figure, we show pressures on the surfaces of the landing gear. And this is something like the source of the noise. So you can see a lot of the noise at certain frequencies here comes off different parts of the landing gear. For example, the tires, the struts, the pipes, etc., the tubes. The noise can be predicted from this case in the lower right, where on the x-axis we have frequency, on the y-axis we have, of course, some intensity of the sound. And of course, here's different experiments and the predictions from the CFD. Take a second to look at this example. Another famous example, which is the cavity flow, which I just discussed the problem in boundary conditions. Here the flow moves from left to right, and of course there's a turbulent, complicated field that forms inside the cavity. The flow moves uniformly into the domain, and it sheds, and acoustic radiation is generated by the cavity. This acoustic radiation can be visualized in these basically what we view as numerical Chevrons on the left side of the figure. You can see acoustic waves for this particular case are very directional and actually travel in the sideline direction, that is the upstream direction of the flow, and they shed sometimes even the upstream direction, which is very counterintuitive for very high-speed flows. This is another famous acoustics problem for cavity flow and is studied today especially in the commercial sector for aeronautics. Another famous acoustics problem is the slat problem. Here we have, of course, an experimental figure where the flow comes from left to right over an open slat on an aircraft wing. These are the parts of the wing, of course, that fold forward to create additional lift. Here you can see that we show a numerical Chevron, essentially, or contours of acoustic pressure of the radiation from the trailing edge of the slat. Today we might develop something called like a slat co-filler to fill this in. As the slat opens, it would fill in this whole area. In the upper right, there are some diagrams, of course, of the fluid dynamic effects, and on the lower right, there's a directivity plot, which is much like the polar plot I explained earlier of the directivity of the acoustic radiation. This is another challenging research problem which many students like to work on. Let's summarize our major points. This is just a tip of the iceberg of the entire field of aeroacoustics and the specific subfield of computational aeroacoustics, which is a subfield of CFD. The field of aeroacoustics and acoustics is very old, and certainly much older than the field of CFD. Today they've merged, and some people who practice CFD are highly specialized in the field of acoustics. They've combined these two things into their own specialty. This was my original focus when I was an undergrad student. I looked at in a research group computational aeroacoustics, and it led to many of my other interests. I hope that through one of these specialized courses you can find one of your interests, or maybe one I'm not talking about, to focus on in the future. This way you can become a very powerful and insightful researcher in that you'll have a very deep knowledge of two particular subjects which you've combined in a new way to find out something amazing and beautiful. Now, CAA or CFD in acoustics requires very specialized methods, and this field is just as big, if not bigger, than CFD itself. It also requires specialized boundary conditions. You'll note that our governing equations are not truly altered. We're still looking at the same Navier-Stokes equations, but in a different way. The analytical methods that have come out of acoustics and aeroacoustics are now today often combined with CFD simulations, creating new and unique semi-analytical or semi-empirical approaches. If you want to talk more about acoustics or CFD, contact me. I'm happy to talk about these subjects with anybody. And this is just a very short presentation to give you an idea of the field. Thank you very much for your time today. I'm Professor Steve Miller.